So therefore, the vector is not just scaled, but it also has gained a component in x direction. That means it has also rotated. And how would you find the angle? It is very simple. So these are the various measurements of the angle through which the vertical vector has rotated. Now, instead of introducing a scaling factor only in the column 2, if I were to introduce both in column 1 and column 2, then now let's try and introduce an off-diagonal term, and let's see how the square space, unit square space, transforms into a parallelogram. Now, I would like to keep the x vector undistorted, or it does not suffer any rotation, it suffers mere scaling, and I would want to rotate the y vector and scale it as well, and therefore I am going to change only column 2, because it was very clearly reckoned in the previous discussion that column 1 would influence the transformation of x and column 2 would transform vector y, that is along y axis. Now, if I use this particular matrix in which second column has one term introduced, that is one of the off diagonal terms is introduced. Earlier both were 0 0. Therefore, the vector y would rotate because it would gain a component in x direction. Now, 1 0 is operated upon by this matrix, then you would clearly see it is 1 into 2 plus 1 into 0. So therefore, it is 2, and then 1 into 0 plus 2 into 0, that is 0. That means the x vector is merely scaled and it does not undergo any rotation. When the same matrix operates on the y vector, you can clearly see that it gets rotated because it gains a component 1 in x direction, and in y direction it gets scaled. And you can clearly see that it is 0 into 2 plus 1 into 1, which is 1 here, and 0 into 0 plus 2 into 1, which is 2 here. So therefore, the vector is not just scaled, but it also has gained a component in x direction. That means it has also rotated. And how would you find the angle? It is very simple. You can see that the total magnitude of the vector has now become root 5, or you can also use this particular definition, that is tan theta is nothing but its x component divided by y component, or if you want to express in terms of cos theta or sin theta, you can in fact express as follows. Since the hypotenuse is root 5, which you can see in the figure, and the adjacent side is 2, you get this. And if you are talking about sin theta, then obviously it is 1 by root 5. So these are the various measurements of the angle through which the vertical vector has rotated. Now, instead of introducing a scaling factor only in the column 2, that is distorting factor only in column 2, if I were to introduce both in column 1 and column 2, that is the factors that bring about the rotation of the vectors, then the parallelogram would have been a rhombus. Now, since we introduced the distorting rotating term, or sometimes people call it as shear term, I did not want to use that term because it sounds very familiar to engineers. So if you were to introduce shear terms in both these elements, that is earlier these were 0 0, So in the off diagonal, if you were to introduce shear terms, equal shear terms, then it would have been a rhombus. And if you were to introduce non-equal shear terms, it would have got distorted into a general quadrilateral. So it is very simple. To sum up, I introduced an off diagonal shear term in our distortion term in the column 2, and that not only scaled the y vector but also rotated because it gained a component 1 in the x direction, and as far as the first column remains the same, so therefore we just get a scaled vector in x, and these two modified vectors or scaled vectors go to define a parallelogram space. So let's continue.